Okay, thank you, Nick. Paul, thank you for that fantastic talk. Really appreciate it. So continuing in this theme that I think Nick and Paul and even the poster session has sort of laid out, what we're going to do now is a panel session to really introduce some of our new core faculty to you. A lot of them are up here on the list. So we're really, as Nick has indicated, we're really excited about the 12 dual hire, interdisciplinary hires that we've had so far. And we want to give them an opportunity to introduce themselves to you, talk a little bit about what they do, and just allow a little groundswell of collaborative research energy to develop. So let me call them all up here, please. And I will, come on up, guys, gals, everybody, come on up. So this is, please. It's a tight squeeze. Apologies for that. These are our most recent hires. And the way we're going to do this
okay, so
is we're going to give each one of them a few minutes to talk and tell us a little bit about their work. As I noted, we've hired 12 of these joint faculty, but these are our most recent hires, and they haven't had a chance to introduce themselves to the university so much, and so we're really grateful that they were able to take the time today. We're going to go alphabetically, so Milan, you are going to be first.
All right, thanks a lot. Thanks for coming, and thanks for having me here, Ben. So my name is Milan Ćurčić. I'm a recent hire in the Ocean Sciences Department at the Rosenthal School. And a core faculty at IDSC. So my main expertise is in ocean wave physics, but I'm very much by nature and by affinity a generalist rather than a specialist. And I keep and nurture a broad diversity in methodology in my own work. So I started off in my PhD studies at the University of Miami, which I started in 2009, also at the Rosenthal School. I started as a numerical model developer. So basically, we all weather forecasts. And weather forecasts under the hood, they're made by really large software that runs on many interconnected computers, basically large supercomputing clusters. And they basically solve a system of partial differential equations on a globe or on a region. Now, ocean circulation, which is also very important for both weather and climate, basically solves for a very similar equation set, except one key difference between ocean and atmosphere. In the ocean, we have salinity and we have liquid water, whereas in the atmosphere, we have air that has humidity and condensation, clouds, rain falling out of clouds, and so on. But in between them, we have, at the ocean surface, we have waves. So that's a mechanical kind of perturbation of the ocean surface. So that's where my main expertise and interest is, in the physics of ocean waves, both at the small scale, so the specific physical processes of wave growth due to wind, and also when waves become too steep, when they break, the turbulence that they induce in the near surface ocean layer. So basically, ocean surface waves connect and mediate the momentum transfer between the wind and subsurface ocean currents. So on small scales, they're important for weather and for ocean circulation. For example, when you have a hurricane propagating over the ocean, strong winds generate waves. Waves grow. They grow very high, to tens of feet high, even, and hundreds of feet long, typically under a hurricane. And when they break, they inject very strong, a large amount of momentum into the ocean, which acts to stir the upper ocean circulation, bring the cold water from deep up to the surface, which basically cuts off the energy supply to a hurricane and causes it to dissipate. So that's just one illustration of how the mediation of wave momentum and the response from the ocean is important for the evolution of tropical cyclones, which is very relevant both to us here and also all the coastal communities around the world. I mentioned my broad diversity in approaches. So I started off as a modeler as a student, but over time in my career I have evolved to more observational work. So both consuming observations, but also creating my own measurements in the laboratory. So for several years I've been a member of the Sustain Laboratory on the Marine campus. And the unique thing about the laboratory is that it's the only place in the world where you can generate Category 5 force winds in a laboratory over mechanically generated waves. And we put a variety of sensors in that lab to give us a controlled environment and really study the processes that are otherwise in the field very difficult to capture. I also, besides the numerical and observational work, I also have recently started incorporating theory in better understanding ocean wave physics. So really what I think I bring the most, like what I see as my main strength in our scientific community is that I can very easily interact and get integrated in different teams with various specialties. I think time-wise, that's good. Thank you.
Continuing alphabetically, Michael.
All right. All right, good afternoon, everyone. I'm Michael Fisher. I'm going to continue the theme of talking about tropical cyclones to some extent. A little bit of background about me. I'm an atmospheric scientist. I'm a native Miamian as well, but I got my PhD from SUNY Albany in 2018, and I was tired of the cold weather, so now I'm back here in Miami. It's good to thaw out. And so I work a lot with observations of tropical cyclones, particularly those collected by NOAA's Hurricane Hunter aircraft. And part of that, I've helped develop a database of about 1,300 unique Doppler radar analyses of tropical cyclone structure. And these Doppler radar analyses essentially provide a three-dimensional CAT scan of hurricane structure. So we have an animation here. On the left is an example of a radar analysis in Hurricane Fiona from a couple years ago. You're looking at the wind speeds at a height of 2 kilometers, so kind of in the lower atmosphere. And so my research tries to better understand which hurricanes are essentially going to become big and bad, undergo a process called rapid intensification, which is basically defined as the top 5% of 24-hour intensity change events. So you can think of it like Hurricane Milton from last year, where it went from tropical storm to Category 5 hurricane in about a day. So clearly the impacts of Category 5 hurricane are be much more significant than a tropical storm. So if we can better understand the processes that lead to these rapid intensification events, that could hopefully aid our prediction of these events. So I'm using these observations to try and understand that, and also want to increase our sample size by using some machine learning methods to create a synthetic radar analyses as well. So that's what you see here on the right now, is a prototype machine learning model I've developed where we're trying to basically replicate the analysis you see on the left. So the model's never seen this analysis before, but on the right, the machine learning model is able to successfully kind of estimate, there's this asymmetry in the hurricane, the stronger winds are in the eastern eye wall, and it gets the peak intensity of the storm right too. So by refining this model, my hope is that we can kind of tackle some of these challenging science questions that we can't really get at with the limited observations that we have. So that's kind of just a big picture. So I'm interested in ways to kind of improve this synthetic analysis approach, and just if you're interested in working on hurricanes, happy to collaborate on that as well.
Thank you, Michael. Next, Khan.
It's great to be here. Thank you for having me here, and good afternoon, everybody. I recently joined January 2025, so I'm very new. And my research is mainly on computational mechanics, but for the last 10 years or so, I'm doing machine learning-based computational mechanics. And I won't be talking about hurricanes or weather, but it's a bit different. My work is mainly in automotive and My technology or the work I do is really try to make your vehicles safer. So for the last 5 years or so, the whole concept of the car has changed, because now we just don't have to protect the passengers, we have to protect the batteries, right? And this is even a bigger problem than protecting the passengers, because passengers don't explode, batteries do. So the way this whole thing is going on, in traditional way, a car is designed, it can take anywhere from a year. But what I am trying to do, or what my research is going on, is introducing machine learning techniques to replace traditional numerical simulations and thus accelerate these predictions. So now, if something that takes 6 months, 8 months to design, with machine learning, you can get that in a day or two. And I think that fits very well with the overall that what we're trying to do right now in the United States of advanced manufacturing and so on. So this is really a very major disruptive technology that we can increase the product development exponentially, because by cutting the development cycle. The other thing then, why do we, we develop these advanced material models, we develop these advanced manufacturing, but why stop there, right? Why don't we try to develop new materials, functional materials that will serve a purpose, whether that be a crash, whether that be any sort of an impact. So my research really uses all the experimental data, numerical data, a lot of synthetic data that's been generated. And there's thousands of these, years and years of this data. It's just sitting in the industrial partners' labs, right? They don't know what to do with them. So we use that to develop these advanced manufacturing approaches. We use that to design safer vehicles, to protect the batteries better. And also, I think the next wave that I see where this is going is to generate functional materials, not necessarily generating a new material, but modifying an existing material to serve a specific purpose better. And I think that overall is going to help this, I would say, big umbrella of advanced manufacturing materials and the performance of the materials. Thank you.
Thank you. Maraid, you're next.
Hi, everyone. My name is Maraid Maloney. Just think of like parade. I know it's not spelled that way. It's Gaelic. Long story. So in addition to being a really proud core faculty member of IDSC, I am associate professor in the Department of Informatics and Health Data Science in the Miller School of Medicine. I got my degree from Chapel Hill. I do need to know if there are any fellow Tar Heels in the house. No, that's sad. Okay. Well, at any rate, so I'm a medical sociologist by training, and my primary research areas are women's health and rural health. My health behaviors that I'm most focused on are sleep, which applies to absolutely everyone, and substance use, which particularly since the pandemic applies to almost absolutely everyone. So in looking at these various health issues, I will give you just a brief overview of my primary research project. That is researching equitable sleep time in Appalachia. One thing that you may not know is that Appalachian United States has some of the worst sleep in the entire nation. So this we know. They have the highest rates of insufficient sleep in the entire country, but we don't know why. So this project, we are collecting quantitative, qualitative, and biometric data on 400 Appalachian adults over a 2-year period, collecting data every 6 months. And at the end of this project, we hope to have some really strong insights into not only why these folks have some of the worst sleep in the country, but what we can do about it. I will say we're excited to be crunching some of our first data, and what we're finding is that loneliness, which is a national epidemic, loneliness, social isolation, lack of social support seem to be some of the leading factors associated with these negative health outcomes, as well as increased substance use. So that's just a little snapshot of my research. I'm always looking for interdisciplinary collaboration. I'm excited. Anna and I are already talking about some work that we're going to do together, so I'd love to talk with anyone else in the room. Also, my incredible colleague, Judith Blanc, I think she had to leave. She has a couple of posters up, some of the work that we're doing, looking at reducing maternal mortality, particularly in Black women. So very excited to be here, and I hope to meet many of you. Oh, I don't know, I'm passing it to
Anna.
Oh, well.
Okay, so thank you. It's so nice to be here. Thank you, Nick, and all the IDSC team for putting this day together. And well, I just joined last fall, and my background is in psychology, mostly specifically cognitive psychology. And before joining here at UM, I spent 6 years leading research on extended realities at Stanford. And my main focus is on how we can use this technology to understand how we learn, how we behave, and how we can change our behavior and learn better using these technologies. So, yes, thank you. So for recent projects, so I'm just wrapping up a project that I'm very proud about because I'm originally from Brazil, as you can see from my accent. And I was able to bring VR for 33,000 students from low-income communities. And we are learning from this project that VR has been helping them to learn about the ocean. So there is, I'm very interested on climate change and how we can change our behavior and learn better and deal better with the ocean. So I have been finding that they have been positive effects on learning, positive effects on how those students, K-12 students, were concerned about the ocean, and also how much they felt, how they felt able to learn. That's something that we call self-efficacy. And then more recently, this is a study I started running about 1.5 years ago. It's a longitudinal study. I'm working with school districts in California to understand how teachers, they select content, how do we implement these technologies in the classroom, in the curriculum, and the long-term effects of this implementation. Because usually XR, that's use the technologies, as you can see there, the headsets, they are focused on 1, 2, 3 sessions of 10, 12 minutes, not longitudinal implementations. So with this study, I plan to understand better how the teachers are using this technology in the classroom, and if the effects are bleeding over to other areas than the only one they are using the technology to. And this one over here, so this is a project, we are just writing the paper right now, I hope the publication to be out very soon, that we conducted here in Florida, and it was before I moved here and really motivated me to be here, where I worked in collaboration with the Florida Atlantic University, and we developed a very realistic simulation of West Palm Beach coast. We used drones to capture images and then had photogrammetry created based on that to show sea level effects on that area. And with this study, we are learning that just learning about sea level rise effects is not enough to change our behavior, but it changes how we perceive the risks of this sea level rise, and that in turn changes our behavior. And finally, and more recently, so I've been working with Kim Greenfielder. Kim is over there taking a picture, and then Waze and Bryson as well. So this is a campus-wide implementation of VR, where first-year students, all of them, they had the experience, not a digital twin, but a replica of the campus, where they could visit, for example, here, the Lakeside Village, and they could learn about the history of UM, they could interact with several areas of the campus, and we are excited to learn about how this had positive impacts of their image of the university and their attachment to the university. So I'm, as Maret said, I'm looking for collaborations. I'm very excited to be here and to learn more about what each of you are doing as well. Thank you.
Hi. My name is Gabriel Regondo. I am a researcher from France and Canada. I got my PhD in between France and South Africa, and I'm a specialist of biogeography. The goal of Aquaix, which is the name of my lab, which is a dependence of the fish-based consortium, and this consortium aim at describing every organism in the ocean with all information that you can find from physiological, genetics, catch, exploitation, and potential use for medicine. And the part of my lab that we want to do is a simple thing. We just want to map the distribution of every organism of the ocean, now and in the future. What do we do is, you can see that on the right panel. Basically what we do is we gathered using machine learning all the information on a species, either from expert, either from observation, either from museum, and we collect them one by one. Once we have that, we run an Ansible machine learning that allows us to know where potentially the species can be found now. And we are using Earth system models to downscale the distribution to 5 kilometers. So that means that we have the distribution of all organisms around the world at 5 kilometer resolution. And then we project it according to climate change scenario, if we are allowed to talk about climate change. And we project that for 2050 and 2100 based on various socio-economical scenarios approved by IPCC, which is the Intergovernmental Panel on Climate Change run by United Nations. And we can predict where the species can go and cannot go, which has huge impact for fisheries, for example, for management at a country level or at a continent level, if countries can agree on managing the stocks together. And obviously, we can predict potential conflict based on the rarity of the species and the economical value of the species. For a more conservation point of view, you can see on the top panel, we can compute the biodiversity of different groups. So here I showed you 4 groups, the main ones, let's be honest, the fish, the mammals, the reptiles, so the turtles, and the corals. But we have 40,000 species going from planktons to mammals. And what do we do with these kind of maps? So these maps can be downscaled at 5 kilometer resolution and can be of use when you want to create new marine protected area, when you want to analyze what is the taxonomical diversity, when you want to, for example, search for, I don't know, you want to develop a new drug for medicine, and you will say, okay, I need a place where there is a lot of biodiversity in order to find intron or exon that will be interesting for my drug. And that's this kind of application that we have. And on the bottom panel, what you see, it's a downscale of the biodiversity in Florida by 2100. That one, Florida. And so if it's red, it's not good. If it's blue, it's okay. So as you can see, Florida is in a perfect shape within 50 years. And this is due to the activity of humans, either fisheries, pollution, or climate change. And that's it. Thank you.
Yes, sounds like a very easy problem, Gabriel. Very easy. Last
Thank you.
but not least, JC.
Thank you. And do you mind if I borrow, because I put in a lot of animations in it?
Sure.
So this actually cues me up perfectly to explain the kind of work that I do. I mostly work on the human dimensions of marine conservation and environmental change. And to give you a succinct example of what the hell that means, I'm going to show you a case study that I'm working on using big data to understand big marine protected areas. I'm going to explain to you some of the data that I'm using to answer some of the questions, and then I'm going to show you how those same data can be useful for many other different questions. So this map here is showing you some, but not all, of the large-scale marine protected areas around the world, all of which, by the way, exclude fishing activity within their boundaries. So you are not...
No, point at the computer. There.
Oh, fancy. No, I was trying to get the laser, but it's too bright. Anyway, you're not allowed to fish in any of the blue or red polygons today. well, actually some of them were defunded, so you can fish in them now, but ignore that point for now. And I'm highlighting the red polygon off the coast of Mexico just because I am from Mexico and I'm working on a project there right now. And I'm going to zoom in on that. So that red polygon is now just a red outline, and I'm showing you the soon-to-be marine protected area. And one of the things that we care about, because we're going to exclude fishing activity, is who is going to be excluded. And the way to do that, you need to be able to track humans. And so that's relatively simple. You just put a GPS on a boat and you can track them, right? And you see a lot of pings. Now, these are hourly GPS locations for a single vessel in 2016, but we don't know when they are fishing. And anybody who's spent time on a fishing boat, sport fishing boat, knows that fishing is not the same as catching, right? You can have very bad days where you did a lot of fishing but zero catching. And so we can feed this information through machine learning models and try to identify which of those positions are actually fishing versus transiting. And if you know which of those are fishing, then you can start to try to rate fishing against catching. I'm realizing that it's not as clear shown now, but instead of all the noise that we now just have the fishing positions, and that's something we can do. But then you can track them in time before the MPA was implemented and after the MPA was implemented. And MPA is just the acronym for Marine Protected Area. And this is really important because one of the arguments against MPAs is, well, you're excluding fishing activities. I am going to lose money, I being a fisher, because I'm not allowed to fish there. One of the counter arguments to that is, well, the fish are going to grow and eventually spill over out of the protected area into the unprotected areas, and you will be able to catch them. Of course, that takes time. The fish has to grow, and it has to be mobility and dispersal, and it takes about 5 to 10 years if it works. And so one of the questions is, were the people that were excluded today the same that can benefit from this spillover effect 10 years from now? Right? That has been the argument. Oh, you'll be fine. In 5 to 10 years, you'll see your investment back. But we don't even know if the people stay long enough to reap the benefits. And so that's something that we can do with this. Using the same type of information, I'm also zooming here in Florida, we can try to understand the overlap between fishing activity, shown in the little pixels in blue and teal, and critical or endangered species habitat. So the red polygon that you see there is Rice's whale core habitat. For those of you that might not be aware, Rice's whale is a new species of whale that was discovered in our backyard, and it's gone from we didn't know it existed or that it was a different species to it's a new species to, oh, it's critically endangered within years. And similarly, again, zooming in on Florida, and I think this map kind of overlaps with what you were showing earlier today, I am highlighting 2 areas in red. Those 2 areas have some hotspots of fishing activity, but they are also right east and due east and due west of the canals that are used to manage the outflow of Lake Okeechobee, which is heavily polluted. So you might start thinking, oh, so is that polluted water going to the area where we are catching our beautiful shrimp and eating it in our shrimp cocktails? Perhaps, we don't know. We can, very likely, yes. But with this data, we can all of a sudden start to track who is doing what, where, and what are the implications of that. And so some of the questions that I'm exploring using these millions of data points is, for example, the distributional implications of marine conservation. Who bears the costs? Who bears the benefits of marine conservation? Is there policy leakage? Sure, you're not allowed to fish here. Do I just disappear from the face of the earth, or do I pick up shop and go and fish elsewhere? Presumably elsewhere where there's less enforcement and less rule of law, and I can use more destructive fishing techniques. This has implications for fisheries management. If we can predict fishing, maybe we can predict catch, and if we can predict catch, we can inform stock assessments that tell us how much fish there's left in the ocean and how much you can catch every single year. And also for climate change, right? You can predict where the habitat of a species will be, but you, using this information, can also predict or understand how humans are going to react to a species shifting. And so if a species is shifting, even if the new habitat is over there, maybe I'm going to fish the hell out of it today before it disappears from my waters. And so I think that's an area of collaboration here that we can explore. And of course, ocean conflict, right? In the end, we have many ways of using the marine environment, not just fishing and not just conservation. There's oil exploration, there's leisure, there's shipping, and these are all competing for ocean space. And I also have some projects looking at the economics of human behavior at sea. So when you give fishermen free fuel, do they fish harder? As in, do they spend more time fishing, or do they go and try to discover new fishing grounds that they can now start exploiting? So that's just brief overview.
Thank you. Thank our faculty, our new joint faculty again. We do have a few minutes for a question or two, and let me start with the audience. Anybody out there that has a question?
So, excellent question, love it. I always like the question on, we are modeling 40,000 species, which is on record, and what about the 200,000 less? So basically, especially with machine learning, you need record. You need to know where the species is. But there is theoretical research on biodiversity and evolution, where you can actually know what type of organisms are there, but we don't know them yet. That's theoretical niche modeling. So basically what you do is that you use AI, you know what you have. Okay, you know you have the planet. You divide the planet not in a geographical space, but in an environmental space, okay? We don't care latitude, we don't care longitude, okay? We care about what temperature a species can live, okay? Then you know how many you know of them. Let's say we have 18,000 species of fish, okay? What about the mollusk? What about the arthropods? What about the bacteria, the cyanobacteria? You can infer, basically, how the environmental space can be divided in theory by the species using basic evolution laws of competition and of adaptation. So theoretically, you could know how many species are there. And there was a beautiful paper made in Science and after in Nature, saying that we know currently in the ocean around 200,000 species described, meaning that there is a taxonomist who saw it, described it, and put a name on it, okay? According to this algorithm based on evolution, we think there is 1 million species that are undiscovered. Dumb question, and that's for you to think tonight. First, do we have the taxonomists? Because taxonomists are more rare in university to describe those species. Second, do we have the economy to go at sea and seek for something that we don't know where it is? And does it worth it? Third, given climate change and the impact on the ocean, those species are still there, are already extinct because of the change of the environment that is so fast. So that's my answer to you. You will follow that on Science.
It's called my research agenda.
Any more questions from the audience? I do, allow me to take the chair's prerogative. I do have a question for all of you. So you've all described very nicely how you're using various AI, ML, data science techniques to advance your specific disciplines. How do you keep up with the cutting edge data science that's being developed? How do you tap into that knowledge to improve what you're doing already? How do you keep track of these things?
I think well, then you're right with the concept, like, I don't write AI algorithms. I use them to solve a problem, right? But eventually when you realize that, oh, you can't solve a problem, you got to go and look at what is coming up with AI, because AI is going much faster than anything that's available right now, right? It's just, I think, at least for my case, where we're looking at manufacturing and all that, the needs decide what type of algorithms that need to exist, and then we go and look and try to figure out, oh, well, this has been done to track language, but let me see if I can modify it to simulate a car crash. That's at least how I do.
Right.
I don't know how the rest.
Yeah, I think similar to general scientific literature in everybody's respective fields, it's impossible to keep up to date with everything.
Exactly.
Like, if I read every relevant paper to me, I will be doing nothing but just reading.
Right.
Similar with AI tools that are rapidly evolving and all the methodology, I think the best we can do is, within the bounds of, the time that we can allocate to keeping up, do the best to be aware. And then there is always a certain time lag from discovery or learning about to actual adoption. And then I think it's a personal choice and style to whether you are an early adopter of a technology, like trying out new things that are just coming out, or you wait to see others in your community adopting it. So what I do is I try to keep up to date mainly with basically the assistance kind of that AI provides, the tooling that aids my own work. And just be aware and also pay attention to what my colleagues around me are doing and talking to them. And yeah, no clear answer, but that's general.
Okay.
I have an easy answer, which is to join IDSC. In all seriousness, there is no better way for me to learn than from my colleagues. And I think truly, as we see on the stage today, these are some of the best, brightest, most cutting-edge scientists. And having these opportunities to learn from my colleagues is really, to me, the best way.
Aligned with what you just said, I think for me is always like, I think about how AI could be implemented on what I'm doing. So, I use virtual reality, extended realities, how we could implement AI, not only on the interaction, but also on the development of the software and hardware. And then I look for colleagues that I could ask questions. So if I'm starting a new project, who can I reach out to and ask questions about that specific problem that I'm trying to solve? And that also, I'm look for those answers also attending conferences. Like today, we have a lot of panels there that gave me so many new ideas of how I can implement some of their work into what I'm doing. So I think networking is such important nowadays because, as he mentioned, like I can't read all day, but someone read a lot about something I want an answer about, so I can just reach out to that person and have a nice conversation.
Fantastic. Anybody else want to comment? Or okay. Any other questions from the audience? All right. Let's thank them again, of course. Break time. Thank you. About 30 minutes, we'll be returning. 30-minute break.